Hello friends, I welcome you in lecture number 19 on complex integration. In this lecture we will discuss one more example on cauchy-integral formula. And now we know that if we have a function f of z which is analytic at every point inside and on a simple closed contour C, and if we have a point z0 which is interior to this simple closed contour C, then complex line integral of f of z divided by z minus z0 along this contour is given by 2 pi I times value of this function f of z at point z0 which is interior to given simple closed contour C. So we will remember this cauchy-integral formula, and whenever we have this type of contour integral in which this function is analytic everywhere inside and on a simple closed contour C, and if we have z0 inside this simple closed contour, then we can apply cauchy-integral formula. So I have taken one more example here. Our function is 3z square plus 2 divided by z minus 2 times z square plus 4, and this is division of two polynomial functions. One polynomial is 3z square plus 2 in the numerator, and in the denominator we have product of two polynomials which is again a polynomial. So we know that polynomial function is analytic everywhere in the complex plane. So if we have division of two polynomials, then it is called rational function in variable z, and rational function is analytic at all those points where this denominator is non-zero. In other words, this function is not analytic at points where z minus 2 is 0 and z square plus 4 is 0. Z minus 2 is 0 if z equal to 2, and z square plus 4 equal to 0 can be rewritten as z square equal to minus 4, and if we use minus 1 equal to I square, then we have z equal to plus or minus 2i. So when z is either 2i or minus 2i, z square plus 4 becomes 0. So this function is not analytic at 3 points: z equal to 2, z equal to 2i, and z equal to minus 2i. Now we check whether all these points are inside or outside given circle, which is circle with center 2 and radius 2. So first we can write that given contour is circle with radius 2 and center 2, and if I want to check whether these points are inside or outside, I will put values of z in left hand side. Suppose I put z equal to 2, then I will have 2 minus 2 equal to absolute value of 0, that is 0, and it is less than 2. This means z equal to 2 lies inside given circle, and when we take z equal to 2i here, then we will have 2i minus 2. So this is minus 2 plus 2i, and if we use the definition of absolute value of x plus iy is square root of real part square plus imaginary part square. So here we will have 4 plus 4, that is square root of 8, and it is 2 times root 2, and it is greater than 2. Therefore absolute value of 2i minus 2 is greater than 2. That means 2i is outside this contour. Therefore z equal to 2i lies outside given simple closed contour C. Similarly, we can check for z equal to minus 2i. If I take absolute value of minus 2i minus 2, then this is equal to square root of real part square, that is minus 2, plus imaginary part square, that is also minus 2. So this also becomes square root of 8, which is 2 root 2, and it is greater than 2. Therefore z equal to minus 2i also lies outside given circle. And if we don't want to go in this way, we can just roughly sketch given circle, and we can see whether all these points are inside the circle or outside the circle. Our circle is circle with center 2 and radius 2. Suppose this much distance is 2, then here I will have 2. This point will be 2i, and somewhere here I will have minus 2i. And my circle is having center 2 and radius 2. So because this much distance is 2, this is 4, and radius is 2, so our circle will look like this. It will pass through origin and it will go in this direction. It will pass through 4 also, because radius is 2 and center is 2. So this is our circle whose center is 2 and radius is 2. And we can see these 2 points are outside the circle, and z equal to 2 lies inside the circle. So now we can write our function as 3z square plus 2 divided by z square plus 4, and in the division we will write z minus 2, because this part, which we will denote by f of z, this is analytic everywhere inside and on simple closed contour C. This is not analytic at z equal to 2i and minus 2i, but they are outside this contour. So this f of z becomes analytic everywhere inside and on given simple closed contour C, and z equal to 2 is interior to this contour C. So now we can write that, suppose we consider f of z notation for this part, 3z square plus 2 divided by z square plus 4. F of z is 3z square plus 2 divided by z square plus 4. Then f of z is, first we write down that f of z is analytic at which points. Then f of z is analytic everywhere in the complex plane. It is analytic everywhere in the complex plane except z equal to 2i and z equal to minus 2i. But these 2 points are outside given circle, which are outside our contour. So from this we can say that f of z is analytic everywhere inside and on a simple closed contour. We require our function f of z to be analytic inside and on a simple closed contour C to apply cauchy-integral formula. And we have seen that z equal to 2 is inside C, or it is interior to given simple closed contour. So therefore by cauchy-integral formula, by cauchy-integral formula, we will have integral of f of z divided by z minus 2 along given simple closed contour. This is equal to 2 pi I times value of f of z at that point which is interior to given simple closed contour. Now we put value of z equal to 2 in f of z to obtain f of 2. So here we will put z equal to 2. So 3 into 2 square plus 2 divided by 2 square plus 4. 3 into 2 square plus 2 divided by 2 square plus 4, that we can simplify as this is going to be 4 into 3 12 plus 2, that is 14, and here we have 4 plus 4, that is 8. And if we cancel out this 4, here I will have 4, and here again I can get 2 cancel, so this is going to be 7 pi I divided by 2. And now we can put f of z here. F of z is 3z square plus 2 divided by z square plus 4, that we substitute here. So therefore integral of 3z square plus 2 z minus 2 z square plus 4 with respect to z along given simple closed contour is 7 pi I divided by 2. So this is nice example of cauchy-integral formula. First you have to check whether you are able to write your function in such a way that you can apply cauchy-integral formula. That is, whether you can write your function in this form, f of z divided by z minus z0, where this f of z is analytic everywhere inside and on given circle, and this point is interior to C. So from this, first we have observed that this, if we take f of z equal to this function, then there is no problem, it is analytic everywhere inside and on this circle, and this point z equal to 2 is interior to this circle because it is the center of the circle, and therefore we are able to apply cauchy-integral formula. So we will continue with this type of problems in upcoming lectures. We stop here. Thanks for watching.